everyone. Good afternoon, good morning. My name is Janine Yetke, Director of Sales and Marketing for Armtec. I want to thank you for joining us today. Armtec is pleased to present today's webinar, Big Digs, Site Development and Underground Solutions for Mining. Our two presenters today are Doug Leach, Manager of International Sales, and Glenn Smith, Sales Supervisor for the Atlantic region, whom I'll introduce shortly. First, some housekeeping items. During the presentation, if you have any questions, there are two ways to ask them. One, raise your hand by selecting the button notated by the raised hand. That will allow you to ask an audio question. Option two is to enter your question into the question log. If you're sitting in a boardroom or with a group of people, please designate someone to collect and input the questions from the group into the question log. We encourage everyone to join in the discussion today. As a reminder, attending this session will qualify you for a 1-hour technical informal CPD credit. For those who have registered directly, we will send out the certificate to the email provided upon login. For those who are attending as a group, please compile your list of attendees and send the attendance list with the following details to webinars@armtec.com. Quickly, I'll give you a brief introduction to Armtec. We're a leading global infrastructure and construction materials company specializing in drainage solutions and precast concrete solutions with 43 locations across Canada. We've got an exceptional product range for mine portals, reclaim tunnels, stockpile tunnels, and heavy haul road bridges. On the screen are some of the major product and market application groups that Armtec supplies. Please see our website for more details. I'd like to formally introduce our presenters today. We have with us two Armtec employees, Doug Leach and Glenn Smith, both with significant experience creating solutions for various mining and infrastructure applications. Doug Leach is a member of the Professional Engineers of Ontario and has extensive experience in the civil and mining engineering field. In his 25-plus years with Armtec, he has been involved in the design and specification of an array of drainage and structural projects and has managed some of Armtec's largest mining projects in almost 20 countries on 6 different continents. Glenn Smith is a certified engineering technologist and has worked for Armtec for over 15 years. He's been involved with the specification of Armtec's engineered products throughout Atlantic Canada and has supervised the installation of numerous large-scale multiplate, bridge plate, and bin wall projects throughout the Atlantic region. Both of them look forward to lots of questions and answers after this presentation. And with that, I will now hand off this presentation to Doug Leach.
Welcome, everyone. First of all, I'd like to review what it is we're going to talk about today. We'll spend time on the use of structural corrugated plate. We'll look at several things to consider in the design of projects such as mine portals, haul roads, and the like. We'll touch on some other topics like corrosion, assembly, and earthquake, and we'll finish up with some questions. First of all, we all know the importance of safety, and let's begin by looking at some of the important aspects of that. Today, you'll see several uses of our product line, their assembly and construction. Armtec products have been developed, designed, and manufactured with thoughtful consideration for safe installation. A quick reminder to all, mining is a great business to be in, and at times it can be very tough. But let's always remember, work safe. All right, let's start with a quick look at some of Armtec's mining projects. At first, we had a haul stream crossing for Moa Nickel in Cuba, a wildlife tunnel crossing at Cortez in Nevada, some of the other projects in Wales, a portal entrance at Taft's Limestone Quarry, Bulyanhulu Mine Portal was indeed a big dig, some 30 meters deep in Tanzania, and one of the coldest portals high in the Tian Shan Mountains in Kyrgyzstan, the Kumtur Mine. And finally, Peru's longest running copper mine, Minera Cerro Verde, in Arequipa. All right, let's get started by answering a very simple question. What is structural corrugated steel plate? We start with hot rolled plate, slit it to the correct length and width, then corrugate it into one of two profiles. The smaller profile showing above is generically known as structural corrugated steel plate. We call it multi-plate. The corrugation is 152 by 51 millimeter, or 6 inch by 2 inch, and was first developed by our predecessor Armco in 1931. Underneath the multi-plate is what is known as deep corrugated structural plate, or bridge plate. If I use the term deep core, it's the bottom corrugation that I'm speaking about today. It is truly a metric corrugation profile, 400 millimeters by 150 millimeters deep, and was launched by Armtec in the 1990s. After the plates are corrugated and punched, they're curved to the shape required. It's this ability to curve the plates which makes the product so versatile. By simply altering the curvature, we make a wide variety of shapes and styles which can be bolted to make the final makeup of the structure. Shapes can include circles, arches, ellipses, and high-profile arches. After galvanizing, the plates are nested and placed on flatbeds into shipping containers. So whether you choose multi-plate or bridge plate, the structure is shipped in conveniently nested bundles, allowing the easy delivery to remote sites. Once on site, the plates are quickly assembled according to the drawings that we supply, and the pile of plates, in this case, becomes a bridge. All right, let's talk a little about a history of the structural plate. Corrugated steel pipe has been around for over 100 years, having been developed in the late 1890s. Some 30 years later, in 1931, segmental bolt structural plates were introduced by our predecessor, Armco. From the 1930s to the 1990s, the multi-plate corrugation served the needs of the industry, but as heavier trucks, wider spans, and more demanding needs arose, Armtec developed deep corrugated bridge plate. Deep corrugated structures are 3 times stronger and 10 times stiffer than traditional structural plate, and that helped extend its use into the heavy mining sector. Increased spans, heavier live loads, and lower cover could be better accommodated with bridge plate. While the added strength is important, extra stiffness also brings an advantage that we're going to talk about a little bit later. A little bit to start on flexible steel design. Any discussion on the design of corrugated steel pipe must begin with the Handbook of Steel Drainage and Highway Construction Products. The original edition was published in the 1930s as the first handbook of culvert and drainage products. Several editions and over 80 years later, the handbook remains the primary source for engineers. The book is published today by the Corrugated Steel Pipe Institute in Canada and is available through there. The gentleman certainly to talk to is Ray Wilcock. Let's review the basic design procedures. In the 1920s, the original design procedure was set forth using Marsden-Spangler formula. Over the years, the design evolved into more sophisticated methods, which recognized crushing and buckling. However, ring compression theory always has and still does remain at the core of the design. In ring compression, a load is applied downward on the structure. The outward flex of the structure mobilizes the passive resistance of the soil and provides support. The thrust is distributed equally around the perimeter of the structure, and the pipe acts as a series of columns, each one in compression. Looking at this in the field, the thin wall pipe is highly effective in supporting actual compressive loads. To that is added an engineered granular backfill envelope compacted around the structure, with the net result we have an economical buried structure capable of supporting significant loads. Let's compare how both flexible and rigid structures depend on soil interaction. They both carry loads, but in a different manner. In the top part of the slide, we see how flexible structures move outward and use the soil for support. Contrast that in the bottom slide, rigid structures are designed for limited deflection and the soil backfill supports less. In short, the stiffness of the structure dictates how the soil around it behaves, and herein lies the reason for the economy of flexible structures. They make more use of the lowest cost construction material, the soil. A final look at this. This is a finite element analysis of buried 12-meter span by 4-meter rise, flexible and rigid structures. Bending moments and thrust in the flexible structures are lower, reflecting the distribution of the load into the surrounding soil. Contrast that with the rigid arch on the bottom, where the structure carries much of the load and the moments and thrusts are higher. As discussed earlier, the Handbook of Steel Culvert and Drainage Products has served the primary source for over years for design. Today, the handbook is supplemented by modern-day bridge codes. Both the Canadian Highway Bridge Design Code, which I'll refer to as CHBDC, and the American AASHTO Code have extensive sections on the design of buried structures. The handbook refers back and forth in general terms to CHBDC and AASHTO, but the many tables refer to the AISI method of design, AISI meaning American Steel and Iron Institute. Often heavy mining loads present unique situations that are outside the design realm of any code. In these cases, computer modeling techniques such as finite element analysis are required. In such cases, the principles of various codes are meshed with the design of finite element to meet the associated difficulties with large mining vehicles, high stockpile heaps, and deep portal cuts. Its imperative designs understand the use of FEA, finite element, and how its output can be meshed with the existing design codes. Here is where we at Armtec are able to help in your design situations. One last issue before we get into the use of structural plate. It's important for users and designers to recognize the differences between the deep core bridge plate structures and traditional structural plate. Where we're talking mainly about Canada, it's important to note that deep core products are not manufactured in all countries. And this should be a consideration, especially important for those of you who may operate out of Canada but have mines overseas. All right, we've talked about the corrugation profile differences before. Besides that, bridge plate has thicker steel option, 4.3 millimeters to 8 millimeters. Multi-plate is 3 millimeters to 7 millimeters. Typically, plate lengths in bridge plate are 1.2 meters. You can see that in the picture at the top, while multi-plate may extend from 3 to 3.6 meters per ring installed. Bridge plates are normally used in low cover, high live load, wide spans, and box culverts. On the other hand, multi-plate has a wider range of shapes, typically smaller size structures, but it's much more versatile in terms of manufacturing fittings and curving the plates. So we talked about what 3 times as strong and we talked about 3 times as strong and 10 times as stiff. What does that really mean? Well, let's start by talking about what it means on paper. Here you see the physical properties of 7 millimeter bridge plate and 7 millimeter multi-plate. The red arrows signify moment of inertia, which plays a direct relationship to the stiffness or buckling of the pipe. Check the red arrows. Here we find the moment of inertia of bridge plate at over 27,000 and multi-plate at approximately 2675 millimeters to the 4th to the millimeter, a tenfold difference. Similarly, the purple arrows show the radius of gyration. the desired component of the wall stress, essentially the pipe strength. Bridge plate is 52.85 versus 17 in multiplate, a threefold difference. So the properties bear this out. More importantly, what does this mean in the field? In wider span multiplate structures, there may be a tendency for the roof of the structure to sag unless held in place by cables or struts. It's extremely important for the structure to be held in place for the backfilling procedure. If the structure begins to flatten across the crown, it may attract additional load not accounted for. Multiplate remains a good product for wide spans, but its assembly and shape control before and during backfill can be more challenging. Bridge plate, on the other hand, with its high stiffness, is able to withstand without any cabling or additional support. It's much less sensitive to backfilling as well. All right, so let's take a look at how structural plate products are used in the mining industry. First of all, we're going to look at mine haul roads and some of the considerations for design. These include live load, dead load, the width of the structure, certainly the height of cover, the backfill material available, the span, what's it used for, stream crossing or grade, and also a little bit about earthquake load. Today's mining vehicles continue to increase in size and payload capacity, making the need for careful consideration more important. Today we see vehicles up to 600 metric tons or more, and designers need to know the total weight of the vehicle. And secondly, is the design for loaded or non-loaded weight. The axle spacing is equally important as it defines the location of the load distribution throughout the backfill. Most manufacturers provide this information on their web pages, and you can get that actual spacing there. A new concern has recently come into play. Today's mining vehicles may generate unbalanced load on the structure as it approaches it. Low cover, extremely heavy vehicles are part of this kind of consideration. They'll tend to push this structure over, and this is one of those specific loads that is outside the realm of any design codes and does indeed require special finite element analysis. Now, this isn't something that happens all the time, but it's certainly something to consider if you have an extremely low cover and very high live load vehicle. A couple other less complex but equally important considerations. Two-way traffic on the structure. Keep this in mind. Will there be two structures on at one time? They're heading in opposite directions. Is one loaded? Is one not loaded? Is it full payload, half payload? A good consideration to what the situation would be, this could turn into a more economical solution for your owner. And we need to look at the wheel spacing as well as the axle spacing. The difference between the wheels is equally important as the axle spacing again and distributes the load over the structure. And finally, what is where? Sometimes we get rail on top, regular highway on top, rail underneath, mining structures above and below. This particular structure at Hammersley Iron in Australia had mining vehicles both above and below the structure. Let's look at other loads. Dead load is probably the most important again, and it's mainly a function of the backfill density and its depth above the crown of the arch. In mining, it seems many soil types come into play, and if possible, a good sample is useful to determine the actual density. When actual values are not available, most codes have default numbers which can be clearly identified as part of the design. Secondly, span and rise are probably the most important factors affecting the final design, and ultimately the cost. In the case of stream crossings, good hydrologic data will help size the structure, and the requirements will end up with the most economically available. For underpasses, a realistic clearance box required is always helpful. Thirdly, How high can we make the structure? What's the cover over top? Overpass with low cover are generally economical for traffic flow, but costs increase as the cover goes down. Now, we all know haul trucks typically operate at maximum grades of 15%, and any means of reducing this can turn into large fuel savings. So we'll try, everyone knows we'll try and keep that cover down, but all of these factors should be examined to provide the most effective solution. Other considerations, certainly the roadway width, single or double lane traffic above and single or double lane traffic through the tunnel. It's the underpass, in the underpass portion, one has to decide, is lighting a requirement? The top length of the structure is also dependent on the type of vehicle and number of lanes. Large haul trucks on the overtop route use much wider lanes and often have earthen berms or gabion walls as control barriers. Structural plate is excellent for remote site projects. Large bridges can be delivered to site very economically, and it's not uncommon to be able to deliver a large bridge on 2 or 3 flatbeds or a couple shipping containers. And finally, there's a design method which promotes soil arching, which is good for high cover applications. In some cases, it's good to use multi-plate here, as it is very good at developing soil arching. A little bit about seismic and earthquake as it relates to the mining sector. Many times, mines find themselves in potential earthquake zones. In Canada, public roads fall under the CHBDC, Canadian Highway Bridge Design Code, and thus require review of earthquake loads. That load is based on inertial forces associated with a seismic event having a 10% probability of exceedance once in 50 years. In CHBDC, the regions are assigned a zonal acceleration ratio, which forms part of the calculation. The methodology for calculating the load is well defined in CHBDC and is based on 2/3 of the horizontal ground acceleration times the dead load thrust. In mine haul roads, the dead load thrust is often small compared to the live load, and it may not be significant. However, it need be checked. For roads on private property, the decision on whether it be included is generally up to the owner. For roads designed under AASHTO code in the United States or other jurisdiction, the rules for earthquake loads apply only within 10 miles of recognized fault lines. Again, this becomes the discretion of the designer and how he wants to use this information. I'd be happy to provide more details on this for those of you who may wish to discuss later. Before I hand it over to Glenn, let's look at why corrugated steel plate products are an excellent alternative for haul roads. First of all, they're extremely easy to maintain. They can be extended in the future if need be. There are no problems with bridge deck freezing. That's extremely important, especially if you have heavy mine vehicles running across the top deck. Life expectancies can generally match to the life of the mine. They're easy to transport to remote sites, and they're a wide range of sizes. At this point, I'm pleased to pass the rest of the presentation into the hands and voice of my associate from the wonderful province of Newfoundland, Glenn.
Good afternoon or good morning, everybody, depending on what part of the country you're joining from. I will begin my portion of the webinar with another use of structural plate products in the mining industry, this time for mine portals. Armtec mine portals are generally constructed of bridge plate or multi-plate to form the desired shape. The most common shapes used for mine portals are high-profile arches and semicircular arches. It is possible, as Doug alluded to design these structures for very high cover applications, if necessary. Mine portals are commonly used to prevent surface water from entering the mine, to provide ground support and safe passage of surface roadways over the mine entrance, and also for egress from ground level to the underground mine face, for equipment and mine vehicles, manpower, ventilation pipes, and also utility lines. Some of the things to consider when designing your mine portal, of course, are your egress requirements, whether you need to accommodate single or double lane traffic, if you need to take special precautions for pedestrian traffic, utility lines, or a combination of all these factors. Another consideration is the location of the mine face. The depth will give you the height of cover loading, which is critical to the design of the portal. It will allow you to set the grade of the tunnel ramp. It defines the structure length and can define the solid rock above the entrance. You will also need to consider constructability, things such as the amount of rock removal, the mine face portal connection, and whether or not you will construct the portal with or without the free flow of traffic into the mine. Other things to consider are if an end treatment is required. These types of end sections include a vertical pre-cut or a vertical elbow. Safety is always an important consideration when selecting a mine portal. Having said that, do you need to include a safe chamber at one or more locations in the portal or allow for any vertical riser access points? These safe chambers shown here are similar to those used at Newmont Gold's Subika mine in Ghana. The size of the rock cut will determine how much select backfill will be required in the engineered backfill envelope surrounding the structure. Acceptable backfill for the backfill envelope, which is commonly referred to as the critical backfill zone, is a well-graded granular with angular grains. Gradation requirements will be shown on your installation drawings, but generally it will be 3-inch or 75 millimeter minus material. This material must be placed in 200 millimeter lifts and compacted to 95% standard proctor density. Armtec's design team can help you select the shape based on a required clearance box, thus ensuring you have the necessary space required in your portal. Again, keep in mind if provisions need to be taken for pedestrian traffic or utility line. As for construction of the portal itself, as shown in the photo in the top left, assembly of the structural plate would begin at the mine face and continue towards the desired entry point of the portal. In the top right picture, you need to ensure to leave enough room around the structure to place and compact the engineered backfill, as these are soil steel structures. However, assuming the rock wall is very stable, the room between the tunnel wall and the rock face can be as little as needed for assembly and backfill. This will help reduce blasting the cut and save the owner money. Compaction near the structure can be done with double drum walk-behind rollers or diesel plate tampers. In the photo at the bottom left, you will see safety spaces have been installed. Then, backfill and compaction proceeds as per Armtec's installation drawings until final grade is achieved. So to summarize our discussion on mine portals, the consultant or owner would provide Armtec with the alignment and clearance box of the portal, the rock portal interface, and the footing design. Armtec will then provide a cross-section shape, footing reactions, assembly, and backfill instructions and specifications. We are also able to provide sealed drawings if required, and on-site supervision by trained field staff. Another application in which we can use structural plate is mine tunnels. Again, multi-plate and bridge plate can be used in these applications, as well as tunnel liner plate. Reclaim tunnels, escape tunnels, conveyor tunnels, and process and utility tunnels can all be constructed using structural plate. As I just mentioned, an alternative to the multi-plate and bridge plate discussed earlier is a corrugation profile we manufacture known as tunnel liner plate.
Got it.
Tunnel liner plate is a corrugated steel, two-flanged sectional lining system designed for use primarily in soft ground tunneling and in relining existing conduits under highways and railroads. One of the advantages of tunnel liner plate is that it can be completely assembled from inside the tunnel and grouted at regular intervals as the tunnel progresses. The tunnel liner plate continually generates ring support, providing a safe launch area for workers and equipment to advance. It is available in a wide variety of shapes and sizes, beginning at 1.3 meters in diameter. Tunnel liner plate sections are also provided in 500 millimeter plate widths. When using structural plate for mine tunnels, certain parameters should be considered. The live load, dead load, and whether there is a varying load condition should be examined. You would also consider what the tunnel is being used for. This will assist in determining what size and shape is required to accommodate the machinery or personnel using the tunnel. Also, will there be pipe racks or conveyors attached to the structure? We would need to consider this during the design stage to ensure these don't introduce unaccounted for stresses to the structure. Lastly, what type of access points, if any, are needed in the tunnel?
It's always just good to know question. Oh, no. What are sister companies?
Do you require an emergency escape route or maintenance or hopper openings? All these variables can be implemented during the design stage. The hoppers shown in the right-hand picture were all designed by Armtec and coated with black epoxy paint for added corrosion resistance.
Apparently we need a lot more of that.
James, I think you're unmuted there now. Next, when looking at escape tunnels, the versatility of Armtec structural plate can provide the owner with a wide range of options. Elbows, hatchways, or safety spaces can be added where needed. We have been involved in the design of many unique applications over the years, so please don't hesitate to ask your local representative for assistance, no matter how specific your site requirements may be. For conveyor and stockpile tunnels, our range of shapes and sizes, combined with the fact we are using segmental bolted plate construction, allows for installation over live lines. Economical designs can be produced when Armtec's engineering team is provided with the actual stockpile height or overburden, as thickness of steel can vary greatly depending on the surcharge over the tunnel. Again, maintenance access points can be added where necessary. The structure on the left is part of a 4-kilometer-long conveyor tunnel in Nevada. Special considerations can be taken to allow for ore to be placed into the tunnel through reinforced openings in the structural plate wall. Reinforced hopper openings are designed by Armtec as per ASTM A998A. In the tunnel on the left, a concrete floor has been poured into a round pipe. This often makes for a more favorable design as opposed to an arch on footings. The designer should always remember to allow proper side space alongside the conveyor to accommodate maintenance needs. As with all other tunnel offerings, process tunnels can be supplied with T's or stubs. These special fittings are designed and shop fabricated to meet the various needs of the client's site. Strict regulations and quality control processes are followed by Armtec at all times. Again, engineered drawings are provided to show the placement and assembly of these specialized components. Next, another important use of Armtec structural plate products is for rockfall protection. Armtec RAISEBORE liners provide a safe, easily installed, and economical lining for raised construction by the boring method. Diameters ranging from 1,200 millimeters in lengths up to 120 meters can be installed using semicircular sections. RAISEBORE liners are constructed using corrugated steel sections in metal thicknesses ranging from 2 to 4.2 millimeters. The sections are bolted together to form a complete ring, and the lining is then lowered into place. The space between the liner and shaft is then grouted to provide protection from falling rock. Using this method of construction, no personnel are required to enter the unprotected portion of the RAISEBORE itself. Armtec RAISEBORE liners can be supplied with a lowering ring, ladders, platforms, steel skids, and other accessories as required. Underground utilities and conveyors can be afforded protection from roof falls using structural plate or tunnel liner plate. In this project at a salt mine, which is the photo on the left, the multiplate was assembled and dragged into place to protect the underground conveyors. It was dragged by remote control mine scoop to prevent human intervention below the potential roof fall. In the photo on the right, we can see a tunnel liner plate which has been assembled. Once the annular space has been grouted, it will protect the tunnel from further rockfall. Now let's take a look at mine access crossings. All corrugation profiles outlined in this presentation can also be used for road and rail crossings. As shown in the picture to the left, multiple structures make excellent low-cover, wide-stream crossings for both mine exploration and servicing. This photo was taken at Sims River in Labrador. Stream crossings under rail lines can be pre-assembled and set into place as the lines progress forward, as shown in the center photo. Large bridge plate round pipes make excellent train crossings for rail lines servicing remote mine sites. The photo on the right was taken at Bloom Lake in Labrador, or near Labrador. I'll now take you through the steps required to assemble a typical bridge plate arch. The arch that I'm showing here was used as a stream crossing. This particular arch had a span of 11.34 meters and a rise of 6.55 meters. The project name is Two Creek and is located in Alberta. The equipment used on this site consisted of one small crane and two man lifts, one large crane, two 4-foot bars, which are supplied with bridge plate structures, drift pins, cable and wire jacks, ear wrenches, and hand wrenches. The first thing to do is to sort the plates on site. This makes it easier to pick the right plate and ensures that there are no errors in the assembly of the arch. It also speeds up assembly time if you can establish a system of which plate to use next. Your installation drawings will use specific terminology to identify various plates used to assemble the bridge plate. An example of this could be a 7H LFP. The plate designation of 7H indicates the net covering length, whereas H is 425 millimeters. LFP denotes a long footing plate. Other abbreviations you may encounter are SFP, or short footing plate, and MBP, or main barrel plate. Here you can see the plates are attached to an unbalanced footing channel made of steel. Armtec manufactures this unbalanced footing channel, and it is installed into the concrete footing by the contractor. We specify the spacing between channels and the entry or re-entry angle. Positioning of the unbalanced channel is key to a successful installation. If you do not install the channel as per the drawings specific to your structure, it may make plate assembly extremely difficult to near impossible, as the bolt holes in the plates will not line up as intended. This particular structure has an 8.9 degree re-entry angle. As you can see in these photos, the first two rings of the structure have been pre-assembled horizontally on a flat and dry staging area. Bolts are to be secured but should not be fully torqued. Lifting the two-ring pre-assembly requires a 4-point lift. An appropriate size crane must be determined by the erector and be capable of lifting the two-ring pre-assembly safely into the footing channels. Armtec can and will provide the weight of these two rings. Once positioned properly, it is bolted into the footing channels. After the first rings, the two rings are...
Just had a question.
Yeah.
Just had a question come in from the last slide.
Yep.
How do you assure the entry angle is perfect at 8.9?
What I've seen a lot of contractors do, when they form up further footings, they actually will put sections of 2x4 across the top of their footing formwork, and they'll actually cut the correct angle for the unbalanced channel into those cross sections. And then basically, essentially what happens, the unbalanced channel, complete with the anchor bolts, will sort of hang there in the correct position. And then you'll pour the concrete around the unbalanced channel and, of course, fill your footing. And then basically it's set into the concrete then at the correct angle. Okay, thanks for that, James.
Thanks.
After the first two rings are in place, subsequent assembly is done one plate at a time, or plate by plate, working up from each footing towards the top of the structure. Partial ring sub-assemblies can be considered, thus reducing the amount of bolting time in the actual work area. Consult your on-site Armtec representative for suggestions. Plate assembly continues here in this photo. As this is a stream crossing, assembly of the plates began at the upstream end to ensure proper plate lap with the direction of water flow. This company used two elevating platforms or man lifts, which was a very efficient method of construction. In locations where this type of equipment cannot be used, scaffolding can be used to access the obvert or crown of the structure. When the sidewalls have been installed from the ground up, the top plate in the ring is the last to be installed. Armtec's quality manufacturing is the key factor in this type of assembly. This photo shows the progression of the arch assembly. In the bottom right, we can see an example of the plate layout drawing. This drawing shows the proper lap details to ensure a proper installation. Here are the two seam types referred to on a bridge plate structure. The terminology, of course, is fairly self-explanatory. Longitudinal seams run the length of the structure, while circumferential seams run around the circumference. You'll also notice here that our plates are 1,200 millimeters wide, as Doug mentioned before, and they contain 3 corrugations. The assembly is now complete. Bolts are checked for the required torque, which is 150 to 250 foot-pounds, or 200 to 350 meters. Backfill cannot be placed until the bolts have the required torque, as the compactive efforts could cause undesirable changes to the structure's dimensions. Once this has been completed, the structure is ready for backfill. Backfilling proceeds with the placement of select engineered granular material in maximum 200 millimeter uncompacted lifts for even the heaviest of vibratory rollers. Fill depth must be maintained approximately equal on both sides of the structure at all times. Care must be taken to not have no more than 2 lifts or 400 millimeter differential from one side of the structure to the other. Material is to be compacted to 95% standard Proctor density. Here's a photo of the finished structure. As you can see, a wire mesh head wall system complete with concrete face panels was selected for the end treatment of this structure. A variety of retaining wall systems are available from Armtec and can be seen extensively in an upcoming Armtec webinar on December 12th, entitled Armtec's Earth Retention Solutions and Overview. This webinar will be presented by Doug Lowry and Ron Perico. So to finish up my portion of the webinar, we will discuss estimated material service life of structural plate. Specifically, I will focus on a coating which we can have applied to our structural plate products to increase the estimated material service life. The last decade has introduced polymer coatings for buried plate structures. Armtec's trade name for polymer coating is StrataCat. Polymer coatings are a second barrier coating applied for further protection of buried elements. Comprehensive research and testing recognizes that polymer barrier coats broadens the allowable range of environmental parameters that are known to negatively influence the estimated material service life of buried steel structures. The 4-step polymer coating process entails a diligent surface preparation to eliminate mill scale, followed by an 8-stage pre-treatment wash of the base steel to ensure optimum adhesion of each subsequent coating layer. This is followed by the application of a zinc-rich base layer to a thickness of 1.5 mils per side. The copolymer is spray applied to individual plates, which then pass through ovens to complete the bonding to the zinc base coat. The Armtec StrataCat product guide can be found on our website search function or through your local sales representative. Here you will see multiplate going through the spray boot at the coating supplier. You can also see the workers with hand spray guns touching up any spots which may have been missed by the automated process. Here are the plates entering through the oven. And here are the plates when they came out of the oven and are ready for shipment. This table lists 5 key environmental parameters that have been identified to evaluate the estimated material service life of buried steel plate. These are pH, resistivity, chlorides, sulfates, and hardness. The broadest range of recommended limits appears for polymer-coated steel. So as shown here, given a pH range of 5 to 9 and a resistivity of greater than 1,500 ohm centimeters, polymer-coated steel has an estimated material service life of 100 years. This table can be found in the recently published Performance Guideline for Buried Steel Structures. This 17-page comprehensive guideline released this past February is published by CSPI, or the Corrugated Steel Pipe Institute, of which Doug spoke to earlier. To complement the guide, it's also supported by a white paper detailing the science behind the document. Both documents are a free download from the CSPI website, and it's www.cspi.ca. A flowchart is presented for designers to follow and step through the process of selecting a coating to meet their application's demands. Any of this material can also be provided by your local Armtec representative. So this concludes my portion of the webinar, and I'll now turn it back over to Janine for final comments and questions. Thank you.
Hi, everyone. Thank you for joining today's webinar and found the information valuable. Our question and answer period is coming, but first I'm just going to provide contact information for our presenters and a few other housekeeping items. Please stay tuned in for a question and answer session in just a minute. For more information on what you've heard today, please contact the local sales representatives by locating them on our website, or feel free to contact one of today's speakers at the following email addresses on your screen. At this time, I'd also like to let you know or remind you about the webinar which Glenn mentioned. We'll be presenting on December 12th, a webinar on earth retention solutions to be presented by Doug Lowry and Ron Perhico. You can register for it directly on our website. Stay tuned to Armtec for our 2015 webinar program. The schedule hasn't been finalized yet, but up-to-date information and registration links can always be found on our website, so keep checking in. We really value your feedback. At the end of this webinar, there will be a quick exit survey. Question 6 will ask you if you're interested in receiving more invitations for Armtec webinars. Please, please, please choose yes. Eventually, we will have to remove people from all emails who do not explicitly consent to receive invites because of Canada's new anti-spam legislation. So if you do choose no, you will be permanently removed from our list. So we really, really, really hope that you choose yes and stay connected to us. You can also follow us on social media. You can get all the latest information on Armtec by following us on Facebook, Twitter, and you can view past webinar presentations on YouTube. Thank you again for joining today. Now we'll go into questions and answers. Please either raise your hand or submit them through the discussion board. Thank you.
How robust is the polymer coating? Does it require a special handling that uncoated CSP would not? And how do you coat the through bolts?
I can speak to that one, Doug, if you like. I've been on multi-plate and bridge plate installations, which have used the Stratacat coating. It's a very robust coating. Sure, we probably wouldn't recommend you actually taking a structure that's assembled and hooking a cable up to it and dragging it along the ground. However, it is very, very, it's a very robust coating. And if in the odd chance or the slim chance that you do damage the coating, there is a field repair kit that can be supplied upon request. As for bolts, right now what we use, as of today, we have no special coating that or polymer coating that will go on the bolts. The bolts will be our standard multi-plate bolts. You can, I believe, opt for stainless steel bolts, Doug, if I'm not mistaken. Stainless is available in 3/4
bolts as well.
Or aluminum bolts, yeah. But right now there is no polymer coating per se on the bolts itself.
Do you require any sealant between the plates to prevent any water leakage?
I guess that'd be a site requirement of the owner, essentially. Bridge plates are shingled, and multi-plates are lapped, but they aren't watertight. We do have seam sealant tape which can be supplied with either multi-plate or bridge plate. I know I can speak to the Newfoundland DOT specifications. If we're doing an install across a stream, it doesn't require waterproofing. However, if we do, say, an underpass on a roadway, it does require waterproofing. So on those structures, we would supply seam sealant tape for either bridge plate or multi-plates. But without it, of course, the structures aren't meant to be watertight. No.
Can you provide a cost comparison and total cost of maintenance costs between multi-plate and bridge plate?
I'll check that one, Glenn. In actual fact, there's really no cost difference in terms of maintenance, and in either case, there's very little cost in maintenance at all. Typically, once the structure is installed, it's covered over, and really the only aspect that gets any kind of maintenance at all might be the interior. You may see over time some very minor depletion of the zinc coating. So as someone can check that perhaps on a 5-year basis, and if they do see a typical kind of depletion of the zinc, there's cold zinc paint that can be applied just to arrest that particular situation. But in the long term, there's really no difference in maintenance between the two, nor is there significant life maintenance as well.
A good question here about codes. With 2 or 3 design methods used, AISI, Canadian Code, and AAS-HTO, which method is used with Armtec?
All right, that's a good question. Of course, the question that Jim was just asked was, when does one use AISI, when does use the CHPDC, and when does one use AASHTO? First of all, any bridge plate application will require the use of the Canadian Code, CHPDC, or AASHTO. That's because it's a stiff structure. There's lower flexibility in it. And CHPDC and AASHTO both contain equations which look at the bending moment in the structure itself. So any bridge plate must use one of those 2 codes. Now for multi-plate, you can use both codes virtually up to any span that you want. Typically CHPDC suggests that it's used up to 3 meters in diameter. AISI use 3 meters in diameter, and larger you go into CHPDC. In the United States, you have to use AASHTO for your design, and elsewhere in the world, other countries, it becomes an issue of what you want to use. We see a lot of AASHTO being used in other countries, or AISI as well, typically up to about 6 meters. So here in Canada, if you're doing a bridge plate, requires CHPDC, and anything else, typically 3 meters and under, is done by AISI.
Thanks very much. A question here about required cover for CSP to protect from a 240-ton haul truck. Is there a specific chart that you guys would issue or share regarding that?
That's a very good question. In the Handbook of Steel Drainage and Construction Products, there are charts available. Those are all based on the AISI code, and they're typically only for typical highway loads that you would find, truck loading. There are no such similar tables for heavy mining vehicles available, so it's one of those situations where you have to look at it individually.
Oh, kind of similar one. Is there a chart that defines the critical backfill zone?
There's not necessarily, I'll take that, Glenn, as well. It's Doug here. There's not necessarily a chart that defines it, but each of the codes specifies the amount of critical backfill that's required. Again, it's a function of the span. Typically, span divided by 2 is one that you may see, or twice the span, excuse me, out each side of the structure. Those, again, are defined a lot of the times in the design by Armtec, and there are also special in the code, such as Canadian Highway Code and AASHTO. They define the amount of backfill on the side as well. So there are not necessarily tables per se, but they are defined in the design codes.
Yeah, and like you say, further to that too, guys. I mean, when you order a structure from Armtec, you will get a complete set of engineered drawings, assembly and installation drawings, and that'll detail out your backfill envelope on those drawings as well.
Looks like that's the end of questions. So thanks all for attending today, and thanks to our speakers. Again, if you are in a boardroom, make sure you take a roster and send an email over to webinars@armtec.com. And for more information, armtec.com/contact us, or you can reach directly to your speakers with the email addresses on screen today. Again, we have one more webinar this year, so hope you'll join us on December 12th, and you'll find out more about that at armtec.com/webinars. Thank you. Have a good day.